I meant to talk about was gravity waves. All right, that's the big thing that was discovered. So that's my talk, is gravity waves. It only took 99 years to find them. It is almost literally 99 years since they were first proposed to when they actually did finally find them. So I'm Professor Nathan Bezayiff, Lone Star College, and this is the communication across the curriculum. All right. All right, so here's a basic outline. Where do they come from in science? Why should we have them at all? What are their properties? How do we detect them? And then also, what are they useful for? Okay, so this is a basic sketch of what we're going to do in this talk. Okay. All right, the first thing we're going to do is okay. Close this a little bit. Commotion outside. Okay. Here. Okay. So the first thing that happens is there's actually something like this that happened in history, so I'll first start with that example. In 1870, James Clerk Maxwell, for his time, showed that all the experiments of electricity and magnetism could produce an electromagnetic wave. And at that time, you had electric charges, so opposites attract and like charges repel. And from the math of his time, he proved that there could actually be electromagnetic waves. Something else that happened at this time is they had measured the speed of light, and he found that his electromagnetic waves propagated at the speed of light. So the inference was light is really an electromagnetic wave. Okay? So what that looks like is the propagation went something like this. And some key parts of this theory of electricity and magnetism first is that you have to have charges that accelerate. Their motion has to change. So if you see those negative charges like in an antenna going up and down, if they're going one way and they switch to go the other, that is a requirement for having an electromagnetic wave. Okay? So if you have your electric charges doing that, that B is a magnetic field. He envisioned a propagation something like this. Okay? It would make an electric field, and then you would get a magnetic field. And so this entity here propagating, this is the electromagnetic wave. And what's special about these has never been seen before. These aren't real matter, these aren't atoms, but they do have real energy. They are really there in space. They are something physical, actually going where we can't see them. So nobody had ever come up with that before in all of science. Okay? So Maxwell at this point thought this was all theory, okay? A really good theory. And so one thing that his theory came up with is that, light, he found electromagnetic waves propagate at the speed of light that had been measured already before then, so therefore that light that we see is electromagnetic waves. And one thing his theory predicted was that you could have, these would be the colors we see, but there could be other colors that exist that we can't see that have always been there, but we never had a chance to find them in the first place, or we never had a chance to measure them. So you could think of radiant, infrared, ultraviolet, X-rays, and gamma rays as other colors. So, for example, the world's greatest Picasso might be some infrared painting, okay? If you want to go shopping, your radio pants might go with your X-ray shirt, right? You could even think about stuff like that. But the important thing is they are other colors that we don't have cones for. And they're real, they're physical in the universe, they're pure energy, and they propagate, okay? And what's the difference between a radio wave and a gamma wave? Simply how fast they shake. So a radio wave is very slow, and then I get faster. And finally, it's the fastest of all. You imagine those electric magnetic fields switching back and forth a lot. Okay? I have another animation to show you that. So that's what light looks like. So if that electric charge shakes fast, I'll make X-rays. If it shakes slowly, I'll get my radio waves. Okay? So we're going to go ahead, come in. I just had the door closed. Yeah, go ahead and open it. There's a bunch of noise in the hall, so there you go. Okay. All right, so we're going to come up to gravity. Gravity, by analogy, is going to do something similar to this. Okay. So those electromagnetic waves shaking back and forth. The next step was actually to find them. Now, Maxwell died around 1875, so he never got to see his theory actually tested. So that's going to be up to Hertz. Okay. So Hertz in 1888, 17 years after this theory. So pay attention to the year here for a minute. I said that gravity waves were predicted almost 100 years ago, and they were found last year. For electromagnetic waves, they were predicted in 1870 and found only 18 years later. I'll explain why electromagnetic waves were so much easier to find than gravity waves. All right, but Hertz actually wanted to see if he could actually find them, okay? So I have a video to show you of that right here. So again, this is the actual experiment. Question is, let's set this up. All right, so I'm going to accelerate my charges here. If there really is these invisible electromagnetic waves traveling here where you can't see it naturally, they will ring the bell if they actually come over here. The frequency that I shake these charges at will be the frequency of the wave, which will shake the bell at the same frequency. Do you guys see how that works? If this bell doesn't ring, there are no electromagnetic waves. Maxwell's theory is wrong. But if that bell does ring, the only explanation you can have is these waves actually did travel through empty space to go here. And so we're going to do an experiment like that with gravity. But first, let me show you how it works with electricity. Okay, so it's about 2 minutes. And ignore all this stuff down here. That's just technical stuff. Okay. So again, this is all technical stuff to the lab, but I want to show you how they actually do it. This is how your remote. This is for the world's first remote control ever built. So there's the charge shaking. Okay. Now for the mirror. There you go. So this is actually a radio wave, a radio color, if you will. A color too low for you to see, but it nonetheless must physically be traveling through there. Okay, so some other tests to prove to you that there is actually real energy going through there. I block it and it can't get through. All right, and the last one. I can actually bounce them off things. Further proof that there is something really physical there, real energy. Okay. So shake the charge, receive the electromagnetic wave. So it obviously had to bounce off of that piece of metal if they really are really there. Okay. All right. So that's electromagnetic waves. Okay, so there we theorize there should be electromagnetic waves from accelerating charges, from charges that change their motion, and then we actually have to do the experiment to prove that that really happens, and so that's the first part of this. Okay, all right, go ahead and move on. Now we start to get to gravity. If you look at these two equations, this is the gravitational force from Newton, 1667. This is Coulomb's force from 1786, all right? So they're about 100 years apart, but they have the exact same mathematical form. So if I have electric charges in here, I can think of mass, which is influenced by gravity, as gravitational charges in here. The distance, if the distance is large, all right, if this is a big number, I get a small force. Everybody see that? If I divide by 1,000, I get a tiny number. So if the particles are far away, they have a weak force. On the other hand, if they're very close together, d is very tiny. And if I divide by a small number, I get a huge force. So charges and masses that are close together have a large force. Because they have the similar equations in nature, they have a lot of the same, well, at least similar phenomenon, okay? So if I'm able to shake charges and get electromagnetic waves in this theory, there's no reason I shouldn't be able to shake masses in this equation, in this theory, and also get gravitational waves. Okay, so that's kind of the beginning of it. One thing to notice, this G and this K, look at the numbers here, all right? So I go to the next slide. Look how much bigger they are. And what this means is the electric force is very easy to see. It's very large. It's $9 billion, if you want to think of it that way. Whereas the gravitational force is 1/100 billionth of a dollar. There's about 10 to the 20 numbers or decimal places that are different here. And a way you can think about that in your life is electricity is very easy to make. In fact, if you comb or brush your hair, you can actually get the water in the faucet to flinch, because that's how easy it is to make electric charges. That's how much stronger the electric force is. That's why Hertz was able to find electromagnetic waves just on his own desk in the lab, because electricity is a very strong force that you're able to see. Gravity is very weak. If you think about how large the Earth is, even with all that mass, you can still jump. You can still get separation. It takes a lot of mass for a little gravity, so I can't find the gravity waves as easy on my desk as Hertz could, because gravity is just too weak. I really need some large shaking masses somewhere to be able to find gravity waves. Okay? So that's part of the difficulty with why we're not able to see gravity waves very easily, is they are so weak. Gravity is just such a weak phenomenon. Okay? All right, I'm going to modify the theory a little bit. Einstein in 1915 imagines space-time, so reality as we know it. So we've got left, right, up and down, and out and in as our spatial dimensions. And then time, we view it as a rubber sheet like this by analogy, okay? And he thought that gravity should be modified a little bit. And the idea is if you put some mass or energy into it, this is a new theory of gravity right here that will actually predict the gravitational waves, all right? And what this says, put some mass or energy here, and this will tell you how the space-time reality as we know curves. These are constants of nature, so there's the gravity constant, and there's the speed of light. These are actually very much more complicated than they look. This is really 10 equations, by the way. The 3 spatial dimensions in a time equation. Okay. So I put in my mass or energy, and the space-time is going to curve like this. So now what I can do to get gravity waves is if I shake this mass like a charge on an antenna, that will put out ripples in space-time. Right? It's like I'm plunging a rock in a pond, and the pond water is in fact the waves spreading out. Those are the gravity waves. Okay. So they might look something like this. Okay. So they also propagate the speed of light. You could think of them as gravitational radiation. So just as you can get a suntan from ultraviolet light that you can't see, you could get a suntan from gravitational radiation if it wasn't so weak. Okay? But in principle, it's there. And we think about this as a stretching and compression in space-time itself. So the space-time between you and me is stretching and then compressing as these waves go by. So it's actually like we actually physically get farther and closer to each other as the waves propagate by. Okay? So we'll explore this idea coming up. These are actually what some of the gravity waves look like. So here we see space-time itself. It's going to compress along this axis. Just compress, stretch. It's going to compress, stretch, and then compress, stretch. But while it's doing that, stretch, compress, okay? So things are physically moving farther apart and close to each other. All right? So this is what the actual wave looks like. And so now we actually want to figure out a way that we can possibly detect them. One thing that a lot of people do is they say, why don't I just put a ruler and have some particles spread out, and if the space-time really does stretch, they will automatically get farther and closer as the gravity waves goes by. Do you see how that works? But what the problem with the ruler is, your ruler also will stretch. So you won't see the effect that way very easily. Okay? All right. So here's how we're going to see if there's actually gravity waves. The speed of light from the electromagnetic waves is a fundamental constant of the universe. The universe will adjust space and time itself to make sure that every light wave anywhere travels at exactly the speed of light. Time and space are flexible, adjustable, as long as the speed of light stays the same. Okay? That is got priority in the hierarchy of what doesn't change in the universe. So if I have a gravity wave goes by and it stretches my space-time, okay, if it stretches, I know it stretched because the light took a longer time to go between two different points. If the space-time squeezes so that actually the distance shrinks between 2 points, I know that light took a shorter time. So measuring how much time it takes light to travel from one place to the other is how I infer the presence of space-time stretching or compressing. Okay? Okay, so here comes my gravity wave. I come up with a scheme like this. So in this arm here, so here's space-time itself, here's the light ray. So compress, stretch, and while it's doing that, stretch, compress, the light in these two arms will actually take a different amount of time, and I'm going to compare how much time did this light wave travel versus how much time did that light wave travel, and that will tell me how much the space-time has stretched and compressed. One of the light beams is traveling farther if the space-time happens to stretch. The other light beam is traveling a shorter distance as that space-time compresses. So it's kind of weird to think about that actually between you and me, we're actually going farther and closer to each other as the gravity wave goes by us. Okay? All right, this is actually the machine that does this. I'll show you some animations of this coming up. So this is called LIGO. This is a fancy word, interferometer. An easier way to think of it is interference meter. So that's what it really stands for, because we're going to have light waves that interfere. So here's a laser right here. That's the actual laser. Okay. There's one of the mirrors. You've got these mirrors. I'll show you this setup in animation in a minute. And we have a beam splitter here. Is this piece? That's the gravity wave. That's the stretch compress coming down. Do you guys see how that works? So if I go back to there, this is the bird's eye view. Your gravity waves are stretching, compressing, and they're going to come into your L-shaped arm there. And in this case, they're coming down from the top. Okay, so what they're going to do is they're going to stretch and compress this arm, and the opposite time they're going to stretch and compress this arm. The light rays are traveling in these arms. Okay? All right, let me go ahead and show you an animation of this. All right, here we go.
Lasting only a fraction of a second, expanded through the universe.
So here come the gravity waves.
Through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect and correctly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space.
So there's the gravity wave stretch compress coming down from the top.
In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along the 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton.
Okay.
This tiny measurement.
So that's how the actual machine actually works, all right? And they said something interesting there. It is indeed the world's record for the most precise, smallest precision, accurate machine mankind has ever built. If your ruler had, I think, 21 zeros here, you would measure how much that ruler stretched and compressed by 5 millimeters. All right, so nobody has ever built anything as sensitive as the LIGO machine. So there'll be lots of technology for that later, okay? But for right now, the stretch compress comes in like this, and that alternates. The light is going to take different times to travel through the arms. As I squeeze and stretch the space-time like you saw, the bright spots being bright, dark, that's comparing the two times that the light waves are traveling. And comparing the difference in times, you can compare how much the space-time has stretched between the individual light beams. Okay. All right. Some fun facts about LIGO. So they showed you a picture of it there. There's one in Washington and one actually in Livingston, Louisiana. So if you ever go to New Orleans, you can stop by there. They give you a tour and everything. This part of it itself, actually measuring the gravity wave, goes back 50 years. So Einstein came up with the idea in 1917, and he went back and forth in his life if he believed they existed or not. And a lot of scientists, sometimes they believed in them, sometimes they didn't. And a lot of times scientists said, well, if they do exist, we'll never find them anyway because gravity is so weak. So that was 50 years. Finally, both in Russia and then MIT came with an idea to how you could possibly build a device to actually measure gravity waves. And you can see the timetable here. Funding just for the design took 11 years, all right? Then actually getting the money to build it, 4 years later, construction started. 8 years to build it. Initial runs, testing, make sure it works. We need an upgrade, and that's why it goes all the way to 2015. So actually building this device took 50 years. From concept to actually getting the gravity wave you're looking for was a 5-decade project. Okay? In fact, lots of people who started on this stage did not even live to see it actually be completed, if you can think of it. It's almost like building a cathedral and never seeing the finished product, right? So sometimes it happens in science. Okay? All right, now that we know how to detect them, the next thing is we need to figure out something that makes them. But gravity is incredibly weak. So where can we find something that's massive enough to actually cause gravitational waves and go across 20 decimal places to actually register a number on my meter looking for the gravity waves? Okay. So remind you how weak gravity is compared to electricity. Electricity was easy to find, as we saw with Hertz. Okay. So outer space is going to provide the answer for this. So what we find are actually two black holes that are going to merge. As they merge, these are the accelerating masses. Remember, I needed an electric charge to accelerate to change its motion. Now I need gravitational charges to accelerate and change their motion. Think about two black holes orbiting each other. As they orbit each other, you can see how their direction changes, their motion changes, and they're accelerating. That is the condition that I need to have gravitational radiation. Okay? So how much shaking of these gravitational charges or these masses do we have to have? Here are some numbers. First of all, if you took the Earth and multiplied it by 4, that's about the size of one of these black holes. All right, so a very small region of space. But this small region of space weighs 36 suns. Okay? And then its partner has 29 suns. So that's an awful lot of mass to think about. Moreover than that, not only are they incredibly massive, they're each moving at half the speed of light. So they're moving incredibly fast. All right, it's a ton of energy for them to have. They merged over 1 billion years ago. That was before multicellular life even evolved on Earth. So even before there was real life on Earth, or just basic life, that's when they had merged. They actually traveled across the universe for 1 billion years by the time they reached our gravity wave detector in Louisiana. Okay. If you just did it with your desktop computer, just like the computer I have, it would take 5,000 years to crunch through all the analysis to actually get rid of all the noise that this kind of precision has. And so thankfully they employed 10 supercomputers to do the work. Okay? And everything in here is state-of-the-art to push the envelope of supercomputers. All right? So these are the size of the exotic objects. Super massive, super fast, and you can only find them far away in the universe back in time is the only place you can find the right accelerating masses to create the gravitational waves. Okay, so let me show you that animation, which is actually the first half of the animation I just showed. Okay, and I did it on purpose because I want to do the show you the sources. All right, so here we go.
This is the sound of two black holes colliding and merging. Where did this sound come from? A long time ago, in the distant reaches of the universe, two black holes, each about 30 times as massive as our sun, were locked in orbit and spiraling in towards each other. The only visible traces of this spinning cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in the system was in the form of gravitational waves, ripples in the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of
Okay, so one interesting thing is that as powerful of energy as these are in the gravitational waves, gravity is so weak, they don't actually make much of an effect. Okay? Let me show you some other slides to show you this. This would actually be one of the mirrors in LIGO. And this would be actually show you the black holes. And so what I'm trying to show you here is how the arms that actually detect the gravity waves relate to the actual black hole waves coming in. Okay? So, let's see, put this to here. And all right. So there's my black holes colliding. They're going to give off my gravity waves. This flinching back and forth, that is the mirror going back and forth. That is changing the space-time. The light is changing its time, going longer and shorter as the gravity wave passes. Okay. So here come the gravity waves. So you can see the mirror is actually flinching. The light is there changing. The distance is changing, and so the time is changing. And then there actually is the merging wave goes there. Okay. Okay. All right, and the last part of this is, what could this be useful for? This did not emit any light, so it's not like a star, it's not like an explosion in space, it's not like a blast of X-rays. All of this energy was in gravitational waves, okay? And so the next thing we would like to know is, if we've discovered gravity waves, what could we use them in science? How could we advance civilization, all right? One thing that's important to realize is that everything we know about the universe, all the theories we have about planets and stars and galaxies, come from electromagnetic waves. Here are all the colors that you can't see, except for this band right here. Okay, these are all the colors we can't see. It's not, gamma rays are not really purple, and X-rays are not really, dark blue. They're colors that we can't see. Here are the telescopes that we see for the light waves alone. All right. So most of the universe that we understand comes through us to electromagnetic light. But the problem is, one mystery we have with the universe is that most of the universe we can't see. We only see about 4% of it. We know from watching stars going around galaxies that there must be some other type of matter out there. There's all kinds of speculation about what this dark energy or dark matter could be. But one thing that's impressive about gravity waves is most things don't give off light, but everything has mass and energy. All right? If everything has mass and energy, everything can give off gravity waves. So by measuring the gravity waves coming across the universe, we could actually fill this in pretty well as to what actual matter is really there. They are going to give off gravitational light, as it were, and that is what we could find to see all the invisible objects in space. Okay, so we have not been able to do that with light. We can see stars easy because they're bright, they explode, they have all that fantastic light that is so bright, but we can't see planets. Planets don't give off light. We can't really see black holes or neutron stars unless they're near something bright and having an impact on it. But think about all the matter in there in space that does not give off light that we can't see. Now we can see it because by virtue of just them having mass, they will give off a gravity wave. And I could build a gravity wave telescope like LIGO, if you will, to actually see that matter. Okay. It also gives us a whole new spectrum. If you think about all the technology possible, from radio waves to infrared to X-rays and gamma rays, all that we know about from your remote control to your GPS to your cell phones, that is all based on the electromagnetic spectrum. This is a completely new spectrum based on gravity waves. And it has its own set of colors, none of which we can see because we don't have cones for those, all right? But it's like you have one spectrum of light, now we have a new spectrum of some new type matter, and there's, your imagination can just go wild about what kinds of technology. So we can see, frequencies in here. These would be this are the frequencies we can see right now. The other thing, the gravity waves that we haven't been able to see yet are gravity waves of lower frequency. And this is interesting. If you could imagine a wave taking years to complete its cycle, or millions of years for one wave to go through a complete cycle, that's what a gravity wave can do. Okay? Nobody knows what that could be used for yet. All right? Some of the objects we could study, supernova, rotating neutron stars, all kinds of different black holes, all kinds of galaxies. All of these things would give off gravity waves, and we could really learn a lot from them. Okay? Here's another picture that kind of shows the same idea. So this is where LIGO is right here. And then the lower frequency, the gravity wave, the larger the object I can see, all the way back to the beginning of the universe. Something I think is interesting, nobody has talked about high frequency gravity waves. I haven't seen anything about that. But presumably there would be high frequency like X-rays or gamma rays, except with gravity waves. And that would be useful to speculate on what something like that could be used for. Right now there's no actual use for any of this, okay? But I'm saying if we had a whole electromagnetic spectrum and all that technology, what will a gravitational spectrum do for us that we haven't built a single thing for it yet? Okay. One thing that's always interesting is the universe itself. There's never a shortage of mysteries about the creation of the universe. One thing that's important is if you think about the Big Bang, we think we can only see to around 13.8 billion years or so back. Anything that happened in the early history of the universe, if you think about 3 minutes, right? So if you watch the clock and there's only 3 more minutes, in this region here, there was light, of course. There was electricity and magnetism, but light gets scattered, it gets absorbed, it bounces off things, it turns into other particles if it has enough energy. So even if there was light in the beginning of the universe, it won't give us any information because it's been bounced around so many times. Gravity waves, because they're so weak, are thought not to have bounced around at all. So if we could find gravity waves from space, we could actually hear gravity waves since the Big Bang itself, and we could actually be listening to a part of the something left over from the actual explosion of all space and time and matter that we perceive as reality. Okay, and nobody has ever been able to do that. Hubble telescope, I think, is the one that goes back the farthest to about 13.8 billion years. We can't see anything that happened earlier than that. The gravity waves will let us be able to go into how many decimal places you want before you get a number seconds after the Big Bang. Okay, so that's really exciting, I think, to be able to hear something left over from the creation of the universe. Okay. What exact information? Well, we don't know that yet because we just found gravity waves, but there are a lot of people working on how we could make use of that. Okay. And this ties into a little bit what I talked about before. One thing that happens is violent explosions in space. Again, I'd like to know what's going on in the very core of this. What caused the supernova? What were the pressures? What were the temperatures? What actually made it go? Studying the light coming off. Again, the light bounces around, it gets scattered, and it can even turn into other particles. Gravity waves will go from the core of this all the way out, and they won't be impeded at all. So by studying the gravity waves, I can learn about the very deep center of something as violent as a gamma ray burst or a supernova. Okay? And again, it also will let me study things that are very exotic, neutron stars. None of this weird kind of matter, superfluid, superconductor, vortex things, none of this can be seen anywhere on a lab on Earth. It's purely in space. But the gravity waves, if they can actually travel through here without being disturbed, I can learn a lot about the structure of some of these exotic objects. So those may be find objects I haven't seen. This is called a strange quark star, and there might be other weird objects like that. Okay? Okay. So that's pretty much everything that I had to say about gravity waves, what they are, how we detect them, and what they could be useful for. Are there any questions? I can turn the lights back on. Yes?
How fast did you say gravity waves travel?
They travel the speed of light.
Travel the speed of light. Okay. You showed a pie chart that had a ratio of dark energy to dark matter and had a little bit of visible, you can see, 4%.
Yes.
How's that ratio calculated?
That I do not know, actually, to be honest. That'll have to be another CAC.
A lot of different observations, John, of space.
What's the signature observation that tells you you're looking at dark energy versus the signature observation that tells you you're looking at dark matter?
The signature observation of dark matter is the motion of stars that doesn't match with the known mass of the galaxies that the stars are in.
Okay.
The stars move differently than expected, given the amount of mass there, by a lot. A signature observation of dark energy is the acceleration of the universe. That the galaxies are expanding faster and faster apart. But to actually observe that stuff is very technical, obviously, and a lot of detailed experiments. But those are the signatures for those quantities. That's how they get the ratios.
Somebody else have a question? Yes?
How'd they find the black holes?
That I don't know either, to be honest.
Just look.
They didn't find them. They
No.
detected the supposed gravity waves that passed through the machine.
They're just looking with the machine out there. And
They don't even know the direction necessarily that it came from, I would imagine.
Yeah, you're kind of you're limited because if you look at the actual observatory, let me go back. Let's see, where was that? One thing is you can't turn it like a telescope. It's 4 kilometers long, so it's actually punched in the ground. So my guess is that they must have had some reasoning to why they put it there, is that they were hoping that that part of the sky might possibly have the black holes.
they didn't find black holes
And then point the scope at it.
Gravity waves from them. They got gravity waves and then analyzed their signature and realized they must have come from these 2 black holes. And they detected more like 2 weeks later, so it's not an unusual occurrence. It doesn't seem.
Have they detected any since?
Since
The last one that they detected that you mentioned, the second one?
no, I don't think they've detected more than 2 incidents.
Collisions.
Yeah.
Right. Kind of what you do is you build your apparatus. The Earth is going to rotate. Your telescope is fixed, and you hope that as you're going around, you'll get a blast of gravity waves from somebody somewhere in the universe.
So Birkhoff's theorem says that any spherically symmetric, asymptotically flat, empty space solution of the Einstein equations is the Schwarzschild solution, which does not have gravity waves.
That's because it's not radiating. It has to accelerate.
Even if it's radiated, it has to radiate into empty space, and it would be spherically symmetric and asymptotically flat, and therefore would have to be the Schwarzschild solution. Therefore, there are no spherically symmetric solutions, the Einstein equations, that have gravity waves.
Yes, okay, I see what you mean. Right.
So, for instance, within a supernova,
You have to have
no
some.
gravity waves.
You have to, unless it explodes asymmetrically. If it doesn't explode like a perfect sphere, you can get those extra order moments that you're talking about.
So only the failure to be spherically symmetric, only that part of the explosion that fails to be spherically symmetric would contribute energy towards a gravity wave.
Yes.
That'd be a very small proportion of the total energy of the explosion.
Yes, that's true. Yes.
So you, I think, would be very lucky to detect any gravity waves coming from something so small as a supernova. It would have to be black holes or something. You're talking about something 30 times as big as the sun
Yes.
for this thing, and that was detected. It would have to be something really big.
There are some stars that are bigger than 30, 40, 50 solar masses out there, and they've not yet burned their fuel and come into black holes.
Even if they did, only the part that's asymmetric would contribute to
Yes, you're right. Those,
gravitational radiation, so you'd probably not be able to detect it,
well,
even if it did explode.
as long as it was asymmetric, then and you had the explosion that was not perfectly symmetric, like you said, you could possibly do it. But remember, when you have an idealized case, you always do the math with a perfect spherically symmetric situation. But in real life, it's never perfectly symmetric. And so they're thinking that with the supernovas, that if you can get lucky, well, they got lucky with the black holes to merge also, that if it had a little bit that was asymmetric, like you said, a little bit of a wobble or some instability that didn't make the explosion go perfect, then you could still probably see it that way.
I don't think anybody's speculating that they're going to do that
Probably not.
in the recent.
Yeah, these are also not going to be like next year. These are plans for the grand scheme of things. One thing that they want to build, actually, in fact, it's the cover of the talk. This one out here, they actually want to take LIGO and put it in space. This is supposed to have, at least as far as I know, 1,000 times more sensitivity. So when we have these kinds of projects, kind of the next generation of gravity waves, this is kind of cool. There's the Earth. This is not as big as the Earth. This is drawn too big. But the idea is you would have this series of satellites out there. They would communicate with these triangular lasers. And 1,000 to 1,000,000 times, whatever people are hoping for, probably I think 1,000 times would be the next generation. Then you could start seeing things, detect the asymmetrical explosion of a supernova or something like that. So that's on the grand scheme of things to come later on.
That's actually like, they were supposed to do it. It's supposed to be there almost, their original planning.
Yeah, I don't know where they're at in their development.
Delayed a lot.
Yeah, when I was in grad school, I heard people talking about actually coming up with the actual technical parts, and people were working on that. Different, clocks and timers and things like that, exotic materials. Everything is like $5 million, right? So if you want a special clock, it's $5 million, and then of course it's got all the parts. But they were working on assembling those pieces. But David's right; it's probably decades behind schedule.
It is. It's called Lisa, but I remember when I was in graduate school too. It was like they're going to make Lisa soon, and
Yeah.
anything about it. They keep getting budget cuts and delays.
Okay, now
Yes.
I'm coming at this from took physics, I've had physics, and what you all are saying, I understand what you're saying, but my question is very low level.
Sure. Yes.
So what intrigued me was this part you said about us seeing. So there's something that we're sensing that's out there, and this is going to basically shed the light on whatever it is these
Okay.
are going on, because you said they would be able to see. So
There's two parts that I talk about in the talk. Okay. The first part is that here, when people first realize that the regular colors you see are electromagnetic waves, and the frequency, how fast those waves shake through space, when they realized that, they realized you could have waves that shake slower or waves that shake faster. But nobody can ever see them like with your eyes because we don't have a biological cone. We have the 3 cones for red, blue, and green. Some insects can. Bees are famous for seeing ultraviolet, and reptiles are famous for seeing infrared. Those appear as colors for those animals, but we can't see those.
So this would expose those colors. Is that what you're
Right.
saying?
So with the gravitational waves, what would happen is this is a spectrum based on light. I would get a new spectrum based on the gravity waves, yes. That's what I was trying to show here. By analogy, that we could see, red, orange, purple, green, and light, there would be a whole new rainbow in gravity waves that exists out there, real physical matter, or not matter, real physical energy that could produce colors of a completely new spectrum. So that's one part of it. The other part they were talking about was with the universe, most of the universe being invisible. In fact, that's what John and Dave were talking about. And I can't see that right now with regular light, just regular light coming away. All the telescopes we've ever built, where's that picture at? All the telescopes we've ever built handle some of that, some range, some frequency, some color of just the electromagnetic light, okay? So all we can see is electromagnetic light. But now everything has to have gravity. Anything that has mass gives off gravity. And as long as it accelerates, okay, then when it gives off those gravity waves, I could potentially see all this matter that I don't really know what it is, because if it has energy, it has to create gravity waves or bend space-time.
Can I object to your statement that all things with mass give off gravity waves? If that were true, matter itself would be unstable and not exist.
Well, provided, of course, that they accelerate and stuff like that. The idea...
Something that's accelerating in some kind of a weird, non-symmetric way.
Yes, I understand that.
But not all mass gives off gravity waves. That's not true.
Yes, right. But I understand what you're saying. It has to accelerate and change motion. Yes, that's required. But in principle, a lot of this matter could be found, because a lot of this matter would be accelerating and changing its motion, possibly in ways we haven't even seen yet. That matter, by virtue of its acceleration, or as long as its motion changes, that will give off a lot of gravity waves. That will still fill in a lot of this. One thing it could certainly fill in, what type of matter is this? What kind of atoms are these? Are these large, massive particles? Those kinds of questions. Some of those are bound to definitely accelerate, and they would produce gravity waves that we could see. Yes?
Theoretically speaking, has matter in the history of the universe, has matter or energy ever traveled faster than the speed of light?
As far as we know in science, the answer is no. If there is a reality where that happened, we don't have any theory and we don't have any experiments to see what that reality would look like. You can't ever say no, but right now, even though we're really sure that nothing goes faster than light speed, it just takes one theory or one observation, but we haven't seen anything like that yet.
So then theoretically, the initial expansion of the Big Bang theory works. The initial expansion of the universe at the moment 0.000001 nanosecond.
Right.
It's moving no faster than the speed of light.
Exactly. No energy.
Itself could be stretching faster than light.
Yeah,
but the matter within it and the energy within it isn't transmitted in space-time faster than light. Space itself can travel, points in space can travel apart faster than light. And that's the idea of inflationary cosmology. That's the
It's a really subtle question, John.
So basically, you're saying points can travel faster, but basically those are points in space. So basically,
Space-time.
there's nothing there, but they are defined by a coordinate, and they can move.
Well, space has a particular geometry, and so
Yeah.
it is a thing.
I'm thinking within the space.
The matter and energy within the space cannot travel faster than the speed of light with respect to other matter and energy within the space, but the space-time
But
itself
the
can
space itself
stretch
can
than the speed
expand
of light.
faster than the speed of light.
Which is why there are things that we'll never be able to see, because space is stretching faster than the speed of light, and even if it's coming at the speed of light towards us, the space will stretch faster than that light can move towards us.
It's like if you're in a galaxy and I'm in a galaxy, your galaxy keeps moving away from me. And it moves away from me faster than the light that it emits can ever get to me. I don't know if I've never seen or know anything about any limitations on how fast the space-time expands itself. I don't know what some actual numbers would be as far as, how much would that distance in time increase. I have never seen any numbers or data about that. There's no known limits or no. Is there even a ballpark number for how much that rate is, or is that pretty?
It can be anything.
Yeah.
The matter and energy in the universe and how they cause the space-time to.
So the rate of it.
So literally, it could be thousands of times faster than the speed of light.
Yeah.
Inflationary cosmology.
In
the early
inflationary
moments,
cosmology,
yes.
it's much faster than that, than what you just said. Okay.
And so, in other words, you'll never be able to detect the very beginning. Even with gravity waves.
Right. You might be able to infer some things, though, that you couldn't without They might help you infer things. But
There may be some leftover primordial gravity waves from the formation of the universe.
Right.
Is that the warp speed? Is that the one that the space-time stretch? Is that what it is
Yeah,
actually?
that's what they're
Yeah.
referring to.
Yeah.
The idea that you can somehow control that, and therefore travel through space faster than the speed of light by warping
The
space faster than light speed. Which is not, I don't know, some people say they can do it, like, or they were getting close to being able to do it in small,
Nate,
Where's
since-
Miguel out of better when you need it?
did they?
Since you said the displacement, the stretch of an object because of the gravity wave is 10 to the power of negative 28, because you said and ruler of 10 to the power of 23 will stretch only 5 millimeters.
Yes, yes, it's like that, yeah.
Now, how are they going to guarantee in a space that whatever they put in a space will be so tight and fixed in order to be able to measure that minute?
You have to use, as far as we know, you have to use light waves for right now. So you need something very sensitive like this LIGO. And as long as you can compare light waves in one space-time or one region of space, their time at which if they take a long time, they must have traveled a little farther, versus light waves that went a short distance will take a shorter time. That's the ultimate comparison you have to make.
I think he's asking also why, how could they be so sensitive? It took them how many years to be able to figure out how to reduce all the noise?
Yeah, the noise,
Vibrations to minimum and
it's such a, if you think about those mirrors, they're kind of hanging on a string and they're vibrating, right? That's the whole idea. They'll vibrate if you shoot BBs at the no trespassing sign, okay? And which will register a gravity wave. They'll vibrate if there's like, you know, a bird jumps off the tree near this facility, the mirrors will vibrate and you'll think you saw a gravity wave. So all the years that went into that was getting rid of all those weird types of noise sources we normally take for granted. Something as tiny as an animal or something, that's what took so long. That's why it took 10 supercomputers to figure this out. But it is actually an achievement. I'm glad you brought that up. The fact that you could build something that could measure something so small, that is at this point the world's record for sensitivity on a scientific experiment.
But you said 10 to the negative 28, so for that 4-kilometer length of that lab, probably the movement was what, 1,000th of the nanometer or something like that?
Yeah, it's a number so small I can't imagine.
from the side of the proton, like they were saying.
Okay.
Yeah, there's another, let me show you maybe another number to help. I put it was on this slide here. I didn't really talk about it. Right here, so if you think about this, the distance from Glasgow to Edinburgh, all right, that is how much the space-time would stretch if you think about how sensitive they could actually measure it. So it's like measuring that distance to 17 zeros and then your first one after the decimal point. That's the precision on this machine.
That was my question, how they can guarantee that things in space.
But there's so much noise, how do they know that this is something real? I mean, yeah, they have the two detectors, I guess, but
They have the two.
Well, that's why-
And they have a lot of data analysis, and they know what the signal should look like.
Spent 8 years on the,
what they thought they should see. But they knew what the signal was supposed to look like. They saw it and they said, okay, that's a signal, but how do they know it's actually a signal?
We're gonna have to detect more, but
yeah, I mean, the two events is a good start.
Just a start.
But yeah, you're right. As time goes on, they'll get more and more confident that they see them. So,
There are always skeptics when some discovery happens, and eventually they come.
they're pretty confident right now. So yeah, I don't know. They're but for right now, they think they're pretty solid about it. But you know, who knows? Maybe in time will tell. That could be a false positive. That could happen. But for right now, like there's been 2 other instances, and so you just have to wait and see.
So my understanding is that the Einstein equations have somehow a wave equation built into them.
That's where these come from. Yes, I didn't go over that.
The only way you really get to that point is by looking at the partial differential equations, and you ignore a lot of the, you get rid of the covariant aspects. You're no longer looking at tensorial equations when you do that.
Well, some assumptions you can make that do work. You can't solve that fully, as far as I know, but you can make some approximations. For example, the black holes are very far away, so the waves will have traveled a long distance, so their amplitude has reduced a lot. That gives you a gravitational wave that you can solve. So if we were right next to the black hole, it wouldn't be that easy. There'd be a lot of other things going on. But since we're so far away, and their energy is, is big, it's the right power output, but really it's the distance. They've been traveling for a while, they've reduced to the right amplitude. A lot of those effects that are right near the black hole are now gone.
If you look at a purely covariant wave equation with a space-time metric, you take two covariant derivatives that contract the metric tensor, it could be kind of a covariant D'Alembert, if you will. That's equal to 0 because the covariant derivative of the space-time metric itself is 0, one of the fundamental hypotheses of Riemannian geometry. If that's true, then there are no physical sources for these the tensorial equation for gravity waves. And so I wonder, are primordial gravity waves the only possibility? Because if you look at purely tensorial equations, which is what you would expect would be true physics, you don't have any physical sources.
Well, but remember, those are for right next to where the black holes are actually created.
This is for
But we're far away from them. So we can actually measure them when they're approximated that we're a billion years away. In that, what you're talking about, you can approximate it down, and when you cover that distance, then they actually reduce to something you can predict.
This is Riemannian geometry. One of the hypotheses of Riemannian geometry is the covariant derivative of this space-time metric is 0. So if you do two covariant derivatives and contract, you get kind of a wave equation, but there are no sources because you get 0. There's no so I'm just wondering how they get the equations that they are using are not tensorial.
Right, remember though, it's also a binary system that's accelerating, and we're far away, so they approximate the wave equation to what we can measure.
And so I'm talking about tensorial equations. No fluid sources, no sources at all.
There must be something wrong with that because they're able to measure the gravity waves coming across space that we actually detected.
Unless it's not something real.
We've already detected indirectly since 1973 gravity waves.
Indirectly.
Right, but I'm saying most people don't find the detection of the gravity wave the most interesting part of this whole endeavor, because we've already known they exist since 1973 from indirect
Rotating black holes and whatever.
Yeah, from energy loss, just from physical energy loss. There has to be some mechanism for energy loss that is gravitational in nature,
Why does it have to be gravitational in nature?
as opposed to
What other source of energy would you have?
Well, if you have a black hole rotating around a star, there could be other things going on because of the matter of the mass of the star. Could be in a cloud of gas. I don't know. Any number of possibilities.
Well, the people that won the Nobel Prize for that, I mean, I guess all I can say is they probably were able to subtract all of that out and take into account those different types of energy.
most people find that the technology of this almost more interesting than the gravitational wave. The actual scientists.
Yeah.
You know what I mean? The sensitivity, technology sensitivity, more important than the discovery of the wave. Just
20
because
decimal place accuracy is remarkable.
It's remarkable.
Yes.
21 decimal place.
Yeah.
All right. Any other questions?
Thank you, Nick.
Sure. So, yeah.